Hello, I'm Rich Eisenberg, editor of Inorganic Chemistry. To celebrate our 50th anniversary year, we're having leaders of the field come in and talk with Inorganic Chemistry about what they do and how they got there. Today, our special guest is one of the world's best-known inorganic chemists, Professor Harry Gray from Caltech. Harry has been a leader in our field for a long time and has been recognized by awards from ACS in inorganic chemistry and distinguished service in chemical education, the Priestley Medal, and many other awards, including the 2009 Welch Prize and also the Presidential Medal of Science. Harry, welcome.
Thank you, Rich.
Okay.
Good to be here.
We've been together for a long time.
A very long time.
That's right, because I was a student of Harry's during the very early part of his career. But for our readers and our listeners, tell us a little bit about how you got into chemistry.
Well, I got into chemistry as a kid. I love colors, and colors fascinated me, and I was trying to figure out why grass was green. I was very fascinated by jewelry, by gemstones, and I took a particularly liking to something called Prussian blue, which I could make in the lab by mixing up some iron compounds and with some instructions I got. And I got this Prussian blue, this very deep blue stuff that people have used in ink and so on. And I was trying to figure out what in the world, how could this color be? And so that's what hooked me on chemistry. And I got my own lab. I started buying big bottles of acid from sulfuric acid, that is, and nitric acid from a supply house in Chicago, pretending I was a professor. I was 11 years old, but I would write them notes pretending I was a professor, and I needed these big bottles of acid, and they would send it to me, and I would pour it on my mom's clothes and destroy them, and that's how I got started.
Okay, now from there you went to Western Kentucky and you
Yes.
worked, did some chemistry there. And,
yeah, I worked in synthetic organic chemistry. I hate to admit it as an inorganic chemist, but I got my start in synthetic organic chemistry, learning how to make certain kinds of organic compounds. And then from there I went on to Northwestern, where I met a guy by the name of Fred Basolo, who convinced me that organic chemistry wasn't going anywhere, and inorganic chemistry was just undergoing a renaissance at that time, changing from a field which was primarily concerned with the manufacture of sulfuric acid to very exciting things, and particularly in understanding the colors of inorganic compounds I'd been wondering about for a long time. So that was it. I said, wow, I'm going to be able to understand the color of Prussian blue and a lot of other things that had really intrigued me as I was growing up.
Now you also worked with Ralph Pearson.
Yeah, I worked with
Ralph. That was a marvelous
Yeah, I
time.
worked with Ralph
Tell us about
Pearson.
that.
Well, I worked with Ralph because he was a real brainy guy and intellectual. Fred was more of a hands-on guy who worked with me directly in the lab. And so Fred and I would work together for a few months making compounds and studying reactions, and every 3 months or so we'd go see Ralph and he would explain it all to us. Okay. But he was the guy who kind of guided us through theoretical things and so on, and Fred and I were cooked up stuff in the lab.
Now, after you finished at Northwestern, you actually pursued this interest in color again with.
I was really intrigued, and I just got a glimpse of it at Northwestern because they had they knew a little bit about. It was called the crystal field theory. And they knew a little bit about it, but the pioneers in crystal field theory were all in Europe. There was a guy named Leslie Orgel at Cambridge, and Carl Ballhausen was in Copenhagen. And I wanted to learn about this theory. I wanted to go to a next level to figure out exactly what these colors were due to, what the quantitative explanations were, and so forth. And so I had a choice of going to Cambridge or Copenhagen. I found out the beer was better in Copenhagen, than in England, and so I picked Copenhagen. And we took off and went to Denmark, where I started working on crystal field theory.
Mm-hmm. Ligand field theory, and then you did
ligand field theory.
No,
you're all you got it all wrong, Rich. Let me straighten you out. Crystal field theory was what people were doing then, and it was kind of on its last legs because the model was extremely simple. It was point charges. There were no real molecules. There was no covalent bonding. It was a kind of a physics model. And Carl Balhausen loved that because he was a simple kind of guy who loved simple kind of physics models. As soon as I got to Copenhagen, I knew the crystal field theory was going down because there were all kinds of discrepancies. For example, the nickel aqueous spectrum, which Balhausen wanted me to look at, it was off. You could calculate the nickel spectrum, but it was off. One band was off by 1,800 reciprocal centimeters. And Kliksbøl-Jørgensen had told Balhausen that in order to interpret this, you had to introduce covalent bonding. You had to make the model more complicated. Balhausen resisted that. So he assigned me the job of calculating the nickel spectrum within the pure crystal field theory model, but putting in higher levels and so on. But to do a strict, and I did that calculation. I did it by hand. There weren't any computers to do it. I had to diagonalize all these matrices myself, Rich, and it took me 3 months or so. And after 3 months, I showed that I could get agreement slightly better. The 1,800 wave numbers, I got one wave number improvement, down to 1799. And Balhausen thought this was great and told me to keep going. And I said, no, this is a loser. Then I found a sign error in my calculation. When I corrected the sign error, the thing went back to 1,800. And then I did a few other things. I managed to get slight agreement, but I knew that we had to replace the crystal field theory.
Right. When did you start doing the molecular orbital approach?
Right after that. After 3 or 4 months of doing this, I realized this theory had to be replaced. And so I started working on what we now call the ligand field theory. And that was to hybridize Robert Mulliken's molecular orbital theory with the best parts of crystal field theory. The best part of crystal field theory was preserving the single ion, the metal ion electron repulsion model. The Rockefeller parameter model and so forth. So you can calculate the many electron problem at the central atom. I preserved that. But then I built in the exchange, the covalent exchange, by figuring out how to use Mulliken's model, but to make it for inorganic chemistry. And inorganic chemistry, it was good for organic chemistry, where the charge separation is fairly uniform. But in inorganic chemistry, as you well know, we have metal atoms and we have things like oxides and so forth where the electronegativity differences are huge. So I had to build in a way of compensating for charge separation in the molecular orbital model to hybridize it with the best parts of crystal field theory. And then I worked on this vanadiline problem that you know about, and I published that in the first issue of Inorganic Chemistry. I believe it may be the most cited paper ever in inorganic chemistry. I'm not sure.
I'm told it's not. But
it's not.
But
it
in
must
our
be,
hearts and minds,
it must be close.
Okay. Now
anyway, we developed that, and the rest is history.
Now you then went to Columbia, where you started your early career.
Yeah, and I went against Balhausen. Balhausen told me not to work on complicated problems. Mm-hmm. He wanted me to work on really simple things, and I, of course, rejected that because there weren't any simple problems that were very interesting. I wanted to work on metal carbonyls and metal cyanides and metal nitrosyls. And I wanted to work on ferrocene and, all of these things that were much more complicated, and Balhausen didn't think you could solve those problems. But I went after those, with a core of terrific grad students, wonderful grad students who joined my group, including you. And we attacked those problems, and we wrote some of the top paper, the papers we wrote in that period really, I think, cemented ligand field theory as the way to go for the description of electronic structures of inorganic complexes.
Yeah, one of the areas that I was involved with you was the redox active, the metal dithiolene
Yeah,
complexes.
yes, the dithiolines.
That's right.
That is still going, you know. You know,
Yes.
the Carl Wiechert is still calculating those things, the things that we did in those days. We made all those compounds. And of course, you're the guy who discovered the first trigonal prismatic complexes, and I should be interviewing you.
No, that was...
You did this
there was an
beautiful
element of
work.
luck. That's a different time.
You did this beautiful work on the first molecular trigonal prismatic complexes. But that came out of the dithiolene work, and it was very controversial in those days, as you remember.
Right.
We kept arguing with lots of other people about where the electrons were. Well, you know, we thought there were a lot of, we thought the ligands were non-innocent. They were guilty.
Yeah.
Guilty ligands. Because they were doing redox behavior, and I think people didn't really want to accept that. You remember that?
That's right.
They didn't want to accept that. But now, like what, 40 years later, Carl Wiechert is showing quite clearly that a lot of the ideas we had 40 years ago were really right.
Yes.
And it's taken a long time, but you know, that field is still going. And now you look what's happened to that field. There's catalysts, there's therapeutics, there's all kinds of stuff, materials. It's really blossomed, and so on. So we're very, very proud of that work we did in the 60s at Columbia.
I agree, and despite my affinity for that work, though, I would say that you're probably better known for all the work that you did in biological electron transfer and bioinorganic chemistry.
Yeah,
so tell us how you got
that was a
in.
mistake.
How did you get into that
well,
area?
How did I get
You're one
that
of the
area?
founders of that
Well,
area.
you know, I got to Columbia, and I was told that I was one of the many assistant professors. I was told, you know, but Charlie Beckman, the chairman, my chances of getting tenure were pretty small because they had lots of young people. Of course, I didn't care. I just wanted a chance to do some work. I didn't care whether I got tenure or not, frankly. But 3 weeks, unbeknownst to me, there was a kid at Harvey Mudd named Alan Latham, who was a chemist, a very good chemist. He came from a little town, his family came from a little town in Alaska, Platinum, Alaska, where there's platinum mines. And some of his family, his wife's family, were platinum, big platinum people. And the president of Rockefeller Institute, Detlev Bronk, who admitted all the graduate students at Rockefeller. It was a really classy kind of Cadillac kind of place, country club kind of place of science. Bronk admitted all the students personally, the president of Rockefeller. He would call all the classy places. He'd only dealt with the presidents. He called the president of Harvey Mudd and he says, "Do you have anybody at Harvey Mudd who's worthy of the Rockefeller?" And the president of Harvey Mudd said, "Well, we have a guy here, but he's a chemist. He wouldn't want to come to the Rockefeller because Rockefeller did biology, cell biology." And Bronk, of course, thought Rockefeller did #1 in everything. He said, "Oh, we have a great chemistry department at Rockefeller." Rockefeller didn't have a chemistry department. So Latham showed up at Rockefeller and he was interviewed by Bronk himself. And Latham brought in the biggest piece of platinum you've ever seen. His family gave him this enormous piece of platinum and said, "My son, go off and do platinum chemistry." He had about $100,000 worth of platinum. It's an enormous piece of platinum. And so Bronk didn't know what to do. He didn't know platinum was an element. And so he frantically called Ted Shedlovsky, his buddy, who was a retired guy there, and said, "Ted, what are we going to do? This kid has showed up he wants to do platinum chemistry. What are we going to do? We don't have anything." Shedlovsky said, "I'll call Columbia." He called Jack Miller. Remember Jack Miller?
Sure.
He called Jack Miller, and Jack Miller said, "Hey, I got a solution for you. I got a kid here who just showed up from Copenhagen, and all of his work up to date's been in platinum chemistry. His name is Harry Gray." And so 3 weeks after I had appeared, you know, at Columbia and been told, you know, I didn't have any chance at tenure, Detlev Bronk, the president of Rockefeller, called me up. Phone rang. I said, "Hello." He says, "Professor Gray?" I said, "Yes." He says, "This is Detlev Bronk. I'm the president of Rockefeller." He says, "I'd like to make you a professor." He says, first of all, he says, "Do you know anything about platinum chemistry? I've heard you're an expert." I said, "Well, a lot of my work to date's been in platinum." He says, "That's great. How would you like to be a professor at the Rockefeller?" And I said,
Yeah.
"I love it." He
Yeah.
said, "Well, come over and have lunch." And so I did. I met Latham. They made me an adjunct professor at Rockefeller. which I was for many, many years, as you know.
Yes.
Latham showed me this enormous piece of platinum. I said, let's work on it. So Latham and I went to the lab. We carved the platinum in half. We dissolved half of it in aqua regia to make platinum complexes, and we devoted the other half to make jewelry. Tie pins. So we made some beautiful tie pins out of it.
Yeah.
And so I directed his work at the Rockefeller. That's the story. Over years, we made a lot of platinum stuff. You may have seen some of our work, platinum dithioxylates, which we published and so on. You may have met Alan when you were...
Sure, I did.
You knew Alan Latham, right? You met him because we were going back and forth to Rockefeller. Well, that's how it started. Because all the kids, I gave a graduate course at Rockefeller during every year in inorganic chemistry, to teach inorganic chemistry at Rockefeller. Teach them ligand field theory. Teach them, you know, the color of... tell them that, you know, the beautiful rubies have chromium in them in just the right configuration.
Right.
And I told them, you know, what the star sapphire was, and I told them about, you know, all kinds of gemstones and everything. And they came to me and they said, look, Harry, why don't you apply this knowledge of yours and explaining electronic structure and color, why don't you apply it to biological molecules? Why don't you apply it to proteins that have these colors and we don't know what they are and so forth, iron and copper proteins? They kept after me like that. Chris Walsh was one of them, now a famous professor at Harvard. And Chris kept after me. And finally, I said, well, okay, I think I'll work on this. So I started working on hemerythrin, on worm blood. And I started working on blue copper because Charlie Dawson at Columbia had kept showing me these beautiful blue proteins. They had copper in them. They kept asking me, why are they so deep blue?
Yeah.
Because copper sulfate's light blue. Why are these so deep blue? And I said, Charlie, I don't know. And finally, I sort of got interested through this, and I went into the field. I said, okay, I'm going to go into this field, figure out the colors of these deep blue copper proteins. I'm going to figure out why worm blood is red purple, and why human blood is deep red, and you know, and why octopus blood is deep blue, and you know, I'm going to figure out blue blood, I'm going to figure out red blood, I'm going to figure out red purple blood, and all this stuff. I went into the field then.
Yeah.
I got in the field, I got hooked, and then you know what happened.
Right. Now, you also met at the same time, I think Harvey Sugar was at Columbia as
I
a
met Harvey
postdoc,
Sugar at
and
exactly that time, and we went into it. We went in and we said, we're going to work on iron compounds that are relevant to biology. And so we made a whole bunch of iron compounds. We kept iron in solution with iron. We made these dimers and stuff. We wrote this huge paper, 200 pages or so. We submitted it to JACS on the colors. We did the first oxo-bridged iron compounds. Now these units are all over biology. They have these beautiful sort of wine red colors when they make the oxo bridge. We figured all that out, but we wrote a paper that was so long. We got one of the worst referee reports back in history. Should have sent it to Inorganic Chemistry, sent it to JACS. The referee report, the greatest one I've ever gotten, started like this. It said, "This is the worst paper I have ever read." And it went on and on and on like that. This is a horrible paper. It finally said, this paper is so bad it wouldn't make a passing grade in a junior high school science course. And it went on and so forth. And so we rewrote the paper, sent it back to the journal and got it published. And it's really a landmark paper on the structures of iron in biology and aqueous solution. It went on, and now half of iron biology is this stuff.
Right, and then you picked up on electron transfer in biological systems.
When I transitioned to Caltech.
Right.
I decided that, well, now what are these things doing? Well, what they do is these are the things that make us live in respiration. These are all the molecules that run photosynthesis. And so my students, as usual, the students came to me and said, Harry, let's start working on the real thing here. Let's start working on electron transfer. Bob Holwerder was one. He said, let's get started. Let's use our knowledge of inorganic chemistry to develop some probes so we can probe these proteins that are in the respiratory system and photosynthetic system. So that's how we started in the early 70s. We started probing quantitatively electron flow through the respiratory system and through photosynthesis by isolating the key proteins and then studying them systematically. And then one thing led to another, and then we started thinking, how are the electrons moving through these systems at long range and say the cytochrome oxidase, the terminal enzyme in respiration, because these distances were so long. And all of our inorganic textbooks had the electrons moving very short distances. Henry Taube had taught us that electrons wouldn't move very far. But in these big biological machines, right now you're breathing in oxygen, your blood's taking it to your mitochondrial respiratory system, you're turning it over in milliseconds, and there's no way that could be done by these inorganic models that were in textbooks. And so so our thoughts were there must be something, these electrons must be moving at very long range. And so, as you know, we developed this key experiment where we put a probe on cytochrome C, 20 angstroms, 18, 20 angstroms away from the metal site, figured out laser photochemical techniques to trigger, and we literally watched the electron move over this long distance. That was a really mind-boggling moment when we saw that actually happen. And so we had to completely change all of our thoughts about how electrons can move through proteins. And now, of course, it's old hat. Right. We write these things all the time, but we know the control of electron flow in respiratory and photosynthetic systems is this very distant coupling, the super-exchange coupling at long range that allows these communication systems to be built. But we started those experiments. They started in the early 70s. We started building these systems in the mid-70s. Took us 8 years to build the first system, to do the first experiment. But in 1982, we published the first demonstration of electron tunneling through biological medium. And now, of course, the field has exploded and has led to all kinds of other things. But that's, as you say, that's probably what I'm best known for, is that particular experiment.
At the same time that chemistry was going on, you're also doing, again, very interesting inorganic photochemistry.
Yeah.
And this is with binuclear systems.
Yes.
And looking at...
yes, and you're doing a lot of the great stuff in that area now.
Yeah,
I mean, you're doing the greatest stuff in that area now, Rich.
Yeah, but the platinum pop chemistry that...
but I started it all.
Yeah, that's correct. Now, all right. So let me ask: with all these accomplishments, what would you say is your proudest moment or your proudest accomplishment, and sort of that special moment where you knew, I think I have this problem nailed?
I've had a lot of great moments. I tell you what, the greatest moments I've had have been when students of mine have actually made big discoveries and have come in with their, lit up completely, really excited, grabbing me and shaking me and said, I just found this new reaction. Mm-hmm. I mean, this happened certainly in the distant electron transfer experiment when
right.
Jay Winkler and Dan Nocera and Kathy Yoakum and me, they'd been working for years on this. And they pulled it off, and we had these traces that showed clearly the electron was moving. They were incredible. You can imagine how excited Dan Nocera was. Jay Winkler, of course, was conservative, yes. Wanted to repeat it again 2 or 3 times. But Dan was off the wall with excitement, and Kathy and so forth. Seeing their faces have been the greatest moments. Actually, seeing your face and some of the things you did at Columbia, those have been my best moments. Yeah. Seeing John Alexander's face, seeing Zvi Dori's, and Ed Stiefels, when Ed had done some dithiolene work he was very proud of. I've got a whole bank of moments, but it hasn't been me so much as it's been looking at the faces of my students and seeing just how happy they were and proud as these moments came along. And I'm still getting that. I've got a student now named Kyle Lancaster who's just discovered this new type 0 copper, and seeing him, he's so excited about it. These are wonderful moments, and I'm still having them.
Now, one of the things is you have advised many many students over the years, both as graduate students, as postdoctorals. Many have gone into academic positions. You're the leader in that regard.
125 professors have worked with me. Students are now professors.
What advice would you have for a person starting out today in terms of how do you advise your students? How did you get to have such success coming out of your laboratory?
Being a lousy advisor, that's how. I mean, not telling people what to do. I've never told anybody what to do. But general kinds of excitement and things that we're looking for, but I like to think I let all my students and postdocs figure out which direction they want to go, what direction they want to take. I think the key is developing real independence. All of the people come to my lab have developed enormous independent streak. They tell me off all the time. They love to tell me when I'm wrong. And quite frankly, I like to hear that, because science moves by you try something, and when you're wrong, you admit it and you move on to the next level. But I like to think I develop in my students a lot of strength, that they're not scared of anybody. They're willing to come in and say, you know, Harry, your idea about this is really ridiculous. You've got to change it right now, or this thing you did is wrong. I mean, I think that's very important, to develop this strength of character in the people you work with and so forth. And the people who've come from my lab are all, as you know, all very independent. Look at what they've done. They've all gone in different directions. You can look at all the people who came from my lab. They're doing everything you can imagine now.
Yeah.
And it's not really that closely related to stuff they did with me, not necessarily so. And so I'm very proud of that.
Good. What advice would you have for people starting out in
do what you really want to do. Don't do anything else. Don't go into things for money.
Okay.
Don't just try to follow the money or something. That's wrong for scientists. It may be right for other people, but it's wrong for scientists. Scientists have got to get into stuff that they want to do all the time. They just can't wait to get started on. I can't wait for Saturday morning or Sunday morning when I can get into the lab, you know, and work and so forth, because it isn't work, it's all play. I mean, I've been doing my hobby since I started. I mean, the fact that people have actually paid me for this is outrageous, because I've been having so much fun. If you get into something you really love to do, and you'll know when that is, because you don't watch the clock anymore. You don't watch and hope that, you know, it's time to go home or something. That you hate it when you have to go home.
Are you concerned that there's a certain amount of effort today in terms of application of research as well as fundamental knowledge of a research problem in terms of the funding? So
it's a horrible thing. I mean, but it's not a horrible thing to have your eye on a big goal. I think a goal with big applications of how you're going to help people, for example, and now in energy research and solar energy research. I mean, to have your eye on the big goal of converting our planet into completely renewable energy.
Tell us a little bit
as an example. Well, you know, that's what I'm really working on now. As you know, I've got my solar army now, as you know. I'm recruiting kids from all over the world to search for the best catalyst to split water. And you know, this, you can have a big vision, a big goal for this, but you can also do very fundamental work that's going to lead to application. There are going to be enormous applications of this. But you have to detach yourself from getting involved in applied work too early. You have to make sure you're grounded in the fundamentals of the field first, and that you've checked out all the fundamentals. You can do fundamental research and let the people who know how to do applications do it. But there's going to be more and more crosstalk between pure scientists and engineers. And there is right now. In the solar energy field, it's going great. Now we've got great chances to convert our planet from, you know, oil, gas, and coal, and we're spewing out the carbon dioxide. But there's an even bigger mission. We've got to become energy independent in this country. You can argue about the carbon dioxide and the global warming, get all sorts of political stuff and so forth, but everybody will agree that we have to become energy independent. The only way we can do that is through solar energy. And we've got to figure out how to convert solar energy into fuel economically, and that's going to require an enormous group of bright young people getting into the field, and that's what I'm doing right now. I'm recruiting, as you know, my solar army. You're part of it, and I've got hundreds, and I'm going to have thousands of kids all across the world working on these catalysts, interfacing with grad students and postdocs at Caltech and MIT and other places, but to have this army in colleges and high schools and so forth working on this problem. And it's going great guns right now, as you know.
The scope of problems will change for new investigators going forward today from when you started out. Before, we were looking at electronic structure and fundamental reaction mechanisms and molecular structure.
We still are,
now,
though.
Now we're looking at...
Well, we're looking at electronic structure now and mechanisms and more complex materials.
That's right.
And things that aren't sort of pristine little molecules that nobody cares about. We're now looking at all disordered metal oxide catalysts and alloys and all kinds of things where we don't have good theory yet. And so electronic structure at a different level, reaction mechanisms at a different level. But this is what we have to attack. We have to develop techniques to tease out the electronic structures of these complex materials that are going to underlie the new energy economy of the world.
Is it fair to say that as we go forward and as we tackle these more complex systems, that we will be, as researchers, talking with physicists and biologists and engineers, but at the same time, we really need to have our fundamentals in chemistry well-grounded.
And that's a very good point, and we have to stick to that, because in this interdisciplinary world, it's very easy to lose sight of the fundamentals, any depth in any one area. And you get to the point where the kids can come out and they're sort of monolayer in every area, but they're not deep in any area. That's a huge mistake. We have to figure out how to do this. Well, what I'm doing is recruiting these kids to get excited about science and to say we're going to join up and do it. But then they have a need to know, Rich. They have a need to know. Then they know why they're in a chemistry course, in organic chemistry or inorganic chemistry or physical. Our courses are technically superb, but they're frankly very boring. And if you don't have the need to know, you're not going to go through these physics curricula or chemistry curricula, biology curricula, or engineering. You're not going to do it. But if you have a need to know, if you get inspired early and you're involved in a problem and you're already doing research and so forth, that's why it's so important to get these kids doing research in high schools and colleges, so they will have a burning desire to get in, and then they'll know why they're taking physical chemistry, which is technically a superb course, but nobody's going to go into chemistry if they're taking physical chemistry, if they haven't had the experience of discovery, of real discovery, and wondering why in the world this and that works this way. And they can say, well, you know, if you get in and do this tough physical chemistry course, if you do the mathematics and so forth, you're going to have the artillery, you're going to have the tools to really attack these problems. And it's really the model I had. At 11 years old, I was 11 years old, and I was looking into natural things, trying to figure out what was going on. It wasn't until I was in Copenhagen doing ligand field theory that I finally figured out why certain things looked the way they did. But I had a need to know. All through this, I had a need to know. I knew why I was in these courses, because I had a burning desire to know some of these things, and I knew the only way to get it was to take really tough courses. And the kids who are avoiding these tough courses are making a huge mistake.
Right. I think it's easy to have younger kids in elementary school, maybe secondary school, say wow when you show them a luminol experiment or something like that. But we really need to work on them to go beyond that and say why.
Yeah.
Yeah, and that's
Well, and we
what
have to
you're
dig
saying.
down, because
Yeah.
now we have some programs, K through 6 things, that are getting kids interested. Then there's sort of a gap.
Yeah.
There's kind of a gap until you get in some of the programs we have in some high schools, some colleges and so forth. I think the middle school, they're probably losing out or something, but it may be enough of these kids will be, there will be enough of a wow factor that it'll keep them going. They'll piddle around in the labs. One of the problems, of course, is because the very real safety considerations have really changed the way lab courses have gone and what you can do with kids and so forth. The stuff that I did is incredibly dangerous. When I was making bombs and doing all kinds of crazy things, you can't do that anymore. You can't buy chemistry sets now that have real chemicals in them because they're all too dangerous. And so I don't know how we get around that.
How can we get those kids into our laboratories with our students under supervised conditions and have them enjoy the wonder of chemistry at the same time?
I'm going to let you
stimulate the why.
Look, I'm going to get kids interested. I'm going to let you solve that problem.
Okay.
I'm going to get kids doing all kinds of stuff. I'm not going to worry about that.
Okay.
Somebody else has to worry about that.
Let me turn now. This is our 50th anniversary year. And so I want to turn to inorganic chemistry. The journal started when you started your independent career.
It did. And I published my first work in your journal.
Right. So tell us a little bit about how it was at the start and how you perceive our field has evolved and how the journal has evolved.
It was incredibly exciting at the start, of course, because we had just invented all this new ligand field theory. We had done the first, and this is the we for all the people in the field, not just me, but all of us young people in the field then. We'd had a whole new start. We had a whole new theory. Everything you could publish, great stuff without any real problems. People were supporting us from the National Science Foundation. It wasn't a big problem to get support for your work then, because we had a whole new enterprise going. And of course now the field has changed so much that we've created, from the original inorganic chemistry, we've created about 17 new fields. Bioinorganic, organometallic, solid state, metals in medicine, all these things now. There are Gordon conferences, there's journals. Out of inorganic chemistry now, there's probably 50 journals or something doing things that we'd call inorganic chemistry that have spun out. So it's sort of out of control now. It's a question of what is really central in the field, and how does your journal relate to all these other things that have come out of the enormous success of the field. And so I think you've done a fantastic job of, frankly, of keeping the excitement in organic chemistry by having these special issues on energy. For example, you had a great issue on energy. In fact, you've had a couple. One on making oxygen, which I was involved in with you. That's been a tremendous success. A lot of the others, and so you've managed to deal with this by having special issues and the spotlight on one really important problem. And so I think we're as excited or more excited than we've ever been in the field because of how our field relates to energy, how it relates to environment, how it relates to human health. I mean, the inorganic chemistry now and metallo drugs has taken off. The world's greatest cancer drugs now have come out of our field. And so the excitement is all over the place now. It's just sort of managing it that's the difficult problem, and really presenting the right face to the kids coming out and understanding what the field is all about. But it's I mean, this is our century, by the way. People say, we're going to go from a physics century, the last century, to a biology century, but this is the century for chemistry. Mark that down on your pencil, because chemistry is going to be, and a lot of it's going to be inorganic chemistry, that really underlies all of the stuff we have to do now in energy and environment. And so the spotlight is on us, Rich.
I agree with you completely in terms of the fact that chemistry and inorganic chemistry is the answer for lots of the problems that we're tackling, lots of the challenges.
Yeah, a lot of people think inorganic chemistry is a bunch of rocks.
Right, that's right.
But it's essentially everything now.
The challenge for us and for inorganic chemistry as the journal is how do we keep everybody to see the importance of reporting their latest results in a core discipline journal rather than sort of trying to push the barriers out? How do we also keep the focus in?
Well, I think the special issues you've had, I'd like to give you some more advice, and that is maybe have issues in which you have dialogue.
Okay.
And commentaries and stuff, so people can go back and forth and argue about things. There's nothing better than having a system where you've got 3 or 4 different views on something. You could go from your current model, in which has been very successful, in which you've had special issues that have been tremendously successful. You could go from that to a more issues where you have people with actually different viewpoints on certain key areas like energy and so forth, arguing about things and how we should do them and so on. But I mean, you're the editor. I mean, why are you asking me? That's your job, not mine. I'm going to keep publishing. I'm going to keep publishing great stuff in your journal, because it's you've lifted it up to a tremendous level, and it's a great pleasure to publish in inorganic chemistry now, because the articles are really well handled. They're well done. You've got a terrific core of associate editors who are really smart. Vivian Yam even reads our papers. She reads all of our papers and she corrects things in tables. I mean, are you kidding me? And so, come on.
All right. As we go paperless, and that's the next challenge.
Yeah.
So we're
you know, our library stopped taking hard copies of journals. We're paperless. Everything's electronic.
Yeah.
That's a huge challenge. What are we going to do?
For us, I mean, we're used to looking at paper.
I know.
Younger people, younger practitioners of the trade, they don't look at it.
They just go online, you check a thing online.
Yeah.
I don't know, it's going to change the whole culture, because the idea of sort of browsing a journal goes away now. You only go to, it's a real challenge.
There's
because
a different kind of browsing.
Now you just go for the stuff that's right in your narrow field, and you browse it to get that, and you don't browse anymore. So I think it's going to be a real challenge of how we deal with this paperless revolution. I don't know what the answer is.
I don't think anybody does right now. We have perceptions of how it's going to change, and if we think back 10 years ago, 15 years ago, totally different now than what it was then.
Yeah.
And going forward 10 years, I'm not sure that we can predict what will be the preferred way of gathering knowledge and disseminating knowledge.
Well, there's a core dump going on. There's so much data being collected now worldwide. The management is a huge problem, and there's all kinds of issues, checking things, making sure things are right, or so forth. So there are immense challenges facing us, and I'm not sure how to deal with them. But I'm developing a lot of data myself. Let you guys worry about. I've got my eye on the ball with research I want to do with kids. I got my eye. I'm going to let you solve all these other things, Rich.
Okay. With that, let me conclude this interview and thank Harry once again for a stimulating interview, and hoping that all of you have a chance to see why Professor Harry Gray is one of the world's top scientists. Thank you.